Hello, welcome back. In this video, I'm going to talk about how to curve sketching. So before that, let's talk about what does the graph look like if they're increasing or decreasing. By definition, if the function f is increasing on the interval from a to b, then for any two number x1, x2 in the interval a and b where x1 less than x2, then will implies f of x1 is going to be less than f of x2. Because if you think about what does an increasing function look like. So at these two intervals, let's say this is a and b, for every x, x1, x2, this is fx1, fx2. If x1 less than x2, then fx1 has to be less than fx2. So similarly, if the function is a decreasing function on two different intervals, let's say c and d, when s1 less than s2 less than d implies c is bigger than d. So look at these two intervals. This is our CD interval, and I found 2 points in here, s1, s2. s1 is less than s2. Oh, s1, s2, sorry, I write these two wrong. But now, if you look at fx, fx1 is greater than fx2. Then we say this is a decreasing. But what about the first derivative? If the function is increasing, then the first derivative will be what? Then the first derivative for all of these in this interval is going to be a positive number. If fx is decreasing, going down, then our first derivative is going to be a negative number. So what about second derivative? Second derivative has nothing to do with going up or going down. The second derivative is more like how does the shape go up and how does the shape go down. As you see in here, those two parts is going down. This part is concave down, whereas this part, the original function, is concave up. They're both increasing. So what changed that? It's the second derivative, right? So that means if f is concave up, then the second derivative should be a positive number. And if f is concave down, then the second derivative is going to be a negative number. So now let's make a chart in here. Go up in this way, or go up in this way, go down in this way, or go down in this way. So for the first graph, on the upper left, we have an increasing function. So that means our first derivative is greater than 0. And it's concave up, right? So that means the second derivative is greater than 0. So for the second graph, it's also going up. So the first derivative is greater than 0, it's a positive, but it's concave down. So that means the second derivative is a negative. So for this one, it's going down. First derivative is going to be a negative number. And the second derivative is going to be positive because it's concave up. So in here, second derivative is going to be concave down, and first derivative will be a negative because it's a decreasing function. Okay, so now with all of this information, let's try to draw a graph. Okay, so now I am giving you like the graph we have from our previous x squared minus 6x plus 9x. Let's say x cubed. And 9s. Okay, what would be your first step? Well, the first step is you need to find all those critical points. Well, this function, it doesn't have a restricted domain, so we know that this is going to be an open-ended, so means the graph is going to be go on two direction, right? Going all the way up or going all the way down. So now let's find the first critical point. First critical point, we need a critical number by the first derivative, x squared minus 12x plus 9. And then when you simplify, I have my critical point. This equals to 3 times x minus 1 and x minus 3. So that means our critical point is at x equals to 1 or x equals to 3. So again, I don't know if this is global minimum or global maximum. Well, let's find out. So we use second derivative to find out about that. So the second derivative is equal to 6x minus 12. When we substitute it, I have x at 1 for the second derivative is equal to 6 minus 12, which is negative 6 less than 0. So that means at x equals to 1, the original function is concave down. And then similarly, we found the concavity of the second critical point, which is f equals to 3. This is equals to 6 times 3 minus 12, 6 greater than 0. So that means at x equals to 3, fx is concave up. Okay, so now if it's concave down, that means we're going to have our local maximum. So our local maximum is going to be what? F of 1, that is equals to 4. And then concave up means we will have our local minimum is f of 3 equals to 0. So now let's try to graph these and see what does this look like. When x equals to 1, y equals to 4, and when x equals to 3, y equals to 0. And I know that, hey, at s equals to 1, the function is concave down, and at here, the function is concave up, and we don't have other critical points. So that means when you connect those points together, the function is going to look like this way. And there's no endpoint, that means we can go all the way up and all the way down. So that's how you use derivative to calculate the function. So here is another example. A company's bank balance B in millions of dollars and 2 weeks after releasing a new product is shown in the graph below. And sketch a graph of the marginal balance, the rate at which the bank balance was changing over time. So the marginal balance means they ask you to draw a graph of the first derivative. So now we're given the original graph. How do we draw the first derivative? Okay, so first of all, we know that, hey, if the graph, original graph, is increasing, then the first derivative is going to be a positive number. And then if the graph is decreasing, then the first derivative is going to be a negative number. And at all of the critical points, at critical numbers or points, the first derivative is going to equals to 0. Okay, with all of this information, let's try to draw this graph. So on the graph, you might be able to see that, hey, from the interval from 0 to 1, maybe 0.6 or 0.5 or 0.9, it's fine. Whatever that you've seen it is a decreasing. So the graph at this point is decreasing. So that means the first derivative, the marginal cost, is going to be a negative number less than 0. And then from the second interval, from -6 to maybe 3.3 or 3.2, the graph is increasing. So that means your first derivative is going to be a positive number above 0. And then after 3.2, from the interval 3.2, everything greater than 3.2 to infinity, the graph has been decreasing. Very sad, but that's also true. And your first derivative is going to be a 0, less than 0. I'm sorry, it's going to be a negative number. Now we need to find the critical points. So at x equals to 6, we have our first critical point, which is our local minimum. So that means our first derivative is equal to 0. And then at x equals to 3.2 or 3.1, our first derivative is equals to another 0 because it's a local maximum. So with all of this information, we should be able to draw the graph. So okay, so let's label the axis first. The horizontal axis is x. The vertical axis is not y, it's the first derivative, because they're trying to ask you to scratch the graph of first derivative. And then we know that at 0.6, we will have our critical point, and point 3.2, we have our critical point. And we know that, hey, before 0.6, the graph is negative, right? So that means the graph is going to be below the x-axis. And between 0.6 to 3.2, the graph is going to be above, and after 3.2, the graph is going down. So the graph possibly look like this one. So you may take a look. Here is a question, very interesting question. So in here, you may notice that, hey, there is a maximum at the first derivative graph. What would that be? Well, in our original graph, like say, if this is our fx function, our previous fx function, this is a function of fx. Here is our maximum or critical point occurs at when the first derivative equals to 0, right? So this one, if the first derivative, if there's a critical point at the first derivative, so that means this is going to be your second derivative equals to 0. So when does the second derivative equals to 0? That means there is an inflection point. What is inflection point? So inflection point is when the second derivative concativity change. So in here, let me show you a graph. For our cubic function, this is increasing, right? At beginning, it was concave down, and after partially origin, it's concave up. So the concativity is change. It's all increasing, it doesn't matter. But after this point, the concativity of the graph change. So this is called inflection point of the graph. So that means there is an inflection point in here. So now look at our original graph. Is that an inflection point? Yes, when you increase in it. At beginning it was, so I can draw on the graph, but I can draw in here. So the graph is look like this one, right? At beginning, the graph was increasing with a concave up, right? And then after they pass certain point, the graph is increasing also from 0.6 to 3.2. But they're all increasing, but it's from concave up change to concave down. So that means there is a point where is inflection occurs, let's say around 2. So that means on our first derivative graph, you will see a maximum. Okay, so that's it for today's video. Let me know if you have other questions.